Justin Miller, Rockstar College Physics here. And what do we got on the menu for now? We still got some Gauss's Law, one more nice application. And yeah, we kind of move forward from there. So we have looked at utilizing Gauss's Law for a really simple case that we already knew the answer to, which was that 4-point charge, just to kind of get a grasp of it. Then we looked for another case that we already knew the answer to as well, which was for an infinite line charge. But what did Gauss's Law allow us to do? Well, it doesn't do it with a lot less work. I had to not really worry about any in-depth variable changes and integration and such. It was pretty straightforward once you get the idea of Gauss's Law. And now we're going to do it for one more case, which is the electric field due to an infinite sheet of charge. So you may say, oh, infinite again? Why are we doing infinite if there is really no infinite? Well, it happens that infinite line charge or infinite sheet charge can be really good approximations. You say, well, how can they be good approximations if you're saying it's infinite, right? We already showed that for a segment versus an infinite line that we get two very different results. But if we stay close to a line charge and think about infinite in that extent, well, if I got this line charge that's say, what, half a meter or so, and I say, well, you know what, I'm gonna stay around the center of it, and I'm gonna be really close to it, much, much closer to it than the ends are, respectfully, let's say, then what's the angle that is made between this point and the ends in terms of that angle? That's not exactly 90 degrees, but it's getting pretty darn close. Pretty darn close. And actually, as it approaches 90 degrees, most of the electric field due to, say, over here is over in this direction. There's not that much that's actually a Y component. And likewise from this side, it's mostly along the x-axis. And we already know that those components are going to cancel each other out. So what do we end up getting? A very small contribution overall in the Y direction, if again, we are relatively close to this line charge. So with that being said, the idea of infinite isn't really necessarily saying that, oh, it's only applicable for the infinite case. It can be utilized as a really good approximation for cases that are, well, definitely discrete. We've got a discrete length here. As long as we're relatively close to the line, infinite versus discrete give us around the same results. So that's nice to be able to kind of grasp. And it comes to be pretty important for what we're going to do in this next little tidbit, which I just said was an infinite sheet charge. So we're going to take a plane of charge, a nice flat sheet that's infinite in its dimensions in which it is it's laid out. So we could kind of say that we've got this infinite sheet that's laid out like this. Goes infinite that way, that way, that way, and this way. Nice flat sheet. And then what are we going to talk about? Well, we could start saying, well, what's the electric field above the sheet? Or what's the electric field below the sheet? And how are we going to determine that? Well, we're going to determine it using Gauss's Law. And then we could say, well, as long as we're actually close to a finite sheet, pretty close to it, that the infinite is a really good approximation. And that's going to really be something that we utilize to a large degree throughout certain systems in this course. So let us go ahead and start utilizing this. So we'll say Gauss's Law. And the electric field due to an infinite sheet of charge. All right, so with this infinite sheet, we're going to go ahead and say it has a uniform surface charge density. So let me put that here. Infinite sheet of charge with uniform surface charge density. And that's my sigma, which is charge per unit area, coulombs per meter squared. So we're just saying that that's constant, uniformly spread across the sheet, and it's continuous at that. So what are we going to do with this? Well, we got to use some sort of ideas of how we think the electric field should behave in the presence or due to an infinite sheet to begin with, right? So I'm going to draw this out like this, and it's supposed to be infinite, but that's really hard to draw in 2 dimensions. You just say, well, this keeps on going into the board, keeps on coming out of the board, keeps on going those ways. And what are we interested in? Well, we're interested in, for right now, let's say some distance above the sheet. All right, so we're going to say that at some distance above the sheet, just say that this is the sheet here. We'll say that we're going to be distance above the sheet. And let's call this distance above the sheet some distance, let's just call it A. So this little X there, that's on the sheet, somewhere on the sheet, and then we're a distance A above it. And that's where we want to know what is the electric field at that location. So, what are we going to do with this? Well, we need some sort of Gaussian surface, right? That encapsulates a portion of the sheet through which we can utilize some symmetry arguments and have that the magnitude of the electric field across our Gaussian surface is constant or 0, and that the direction pertaining to the normals of the surface and the electric field are preserved. So, let us think about a couple things, just starting with the above part. So if I'm some distance above it, what do I have to look at? Well, let's just kind of take a sheet like this and say that I'm like right here above the middle of the sheet. What does the electric field look like in the middle, directly above the center of the sheet? Well, I'd have contributions from this side, I'd have contributions from this side, I'd have contributions from this side, and really all points, right? All points over the sheet. But what's going to happen is that there's a high degree of symmetry if we're talking about a finite sheet and being directly above the center of it. We get equal contributions from this side, and this side, and this side, and this side. Right? Well, what does that mean? Well, that means that components that are parallel to the plane of the sheet are all going to cancel each other out, just like we had with the line charge, right? We had all the components that were parallel to the line charge, all the components of the electric field parallel to the line charge ended up canceled out, and we're only left with a component that was perpendicular to the line charge itself. We get the same thing with the sheet. This component cancel each other out this way, and just leave us with something like that. This component and this component cancel each other out this way, only leave something like this. And that goes with everything. So, considering that this is a positive surface charge here, positive surface charge density, we should have that the electric field anywhere above it is straight up, if it's infinite in length, or infinite in its expanse, I should say. If it's discrete, then we have to be directly over the center of it. We're not going to really worry about discrete, we're going to just use infinite. So, if it's infinite, we don't need to say center because everywhere is the center. So what do we have here? Well, if at this location, or really any location, the electric field once again should be straight up. That's it. And again, we're going to go ahead and say sigma is equal to a positive here. Well, that's above it. What about below it? There should be an electric field below it too, right? Because any one little element has a radially outward field, great, but it's the same thing below. We take a point below the midpoint of a well-defined sheet or discrete sheet, and the electric field has to be straight down. because all of the components that are parallel to the sheet have to cancel out. So down below it, we've also got this. So this is something that we've got to be careful of. E hat, we'll say above, E hat below. All right, so we've got that kind of worked out with what we should expect for the directions of the electric field relative to the sheet. Now it's a matter of figuring out what sort of surface, Gaussian surface, we should utilize such that the electric field has a constant magnitude across that surface, or just is zero. Flux is zero, I should say. Anyways, what do we do with this? Well, should stand to reason that if the electric field's straight up because all of the parallel components relative to the sheet cancel each other out, that we should have that as long as we're the same distance above the sheet anywhere, the electric field should have the same magnitude. That stands to reason, right? And likewise, if we're the same distance below it, the electric field should have the same magnitude as the distance above it, just different directions. So that kind of invokes this. If we go ahead and say, well, we could be above the sheet or below the sheet, a distance A. I know that this doesn't look as low, but it's kind of tilted, right? That the electric field across, use a different color here. The electric field, where's red? No red, no red, just ran out. Oh well, we'll try green. It doesn't come through that great. That's okay. So we got this, we got this. So we've got the electric field along this line here should be constant, same magnitude, because we're the same distance away from the sheet everywhere. And likewise, the electric field along this line should be the same as well. All right? And furthermore, the electric field strength here and the electric field strength here should be the same, just different directions, same magnitudes, different directions. So we've got here and here, the magnitude of E hat is constant across these two lines. So then it's a matter of making this into a surface, right? A closed surface. So how are we going to close this up and encapsulate a portion of this infinite sheet charge? And, well, it would actually not be too difficult, because if I extend this out parallel to the sheet, hey, that's still the same distance away A. And likewise, if I extend this out parallel to the sheet, that's still the same distance away A from the sheet. And likewise, I could do this, do this. Those are all the same distance away from the sheet. I could start to close this up. Basically, I have another little sheet here that's on top of the infinite sheet that's just kind of hovering above it. And basically, we've got like our infinite sheet here, and then we're just putting another little sheet on top of it, such that that sheet is the same distance away at all locations. Do the same thing on the bottom. So up on the bottom, this kind of closes up here. Great, and then what can we do? Well, we need this to be a closed surface. So what happens if we just kind of connect these? And say, hey, I'm going to connect that, I'm going to connect that, I'm going to connect how does that work? Dot, dot, dot. That one's a weird one for me. And this one. What do? We make ourselves a little cube there. So let's say that maybe it's not an exact cube, but some sort of encapsulation that has a rectangular aspect to it. So let's say, now I'm going to redraw this a little bit. I'm going to take this cube we just had, like this, and we're going to say, well, this whole distance right here, that's going to be our A plus A. So we've got our sheet, it's kind of split down the middle here, and this is A, so this has to be a total distance of 2A, this right here. So go from here down to there, that's 2A. So then we've also got this distance here, and actually that looks pretty close. So let's just call this, let's just call this B. Let's call it something else. So it doesn't necessarily have to be the same. So we'll call this B. So that's a B right there. And what do we have? We've got one more dimension here. We've got that right there. So what if we just go ahead and call that C? Which would be this, and there we go. So we've got, it's 2A high, it's B wide, and has a depth of C. So that's our rectangular block, we'll say, that encapsulates a portion of this sheet here. All right, so let's think about a couple things here. We're going to have non-zero flux through this top, non-zero flux through the bottom, because the electric field goes actually through the top and through the bottom. What about all these sides in here, right? We've got these four other sides. Right side, left side, front side, back side. What about those? Well, the electric field, again, is going to be parallel to the planes of those sides there. Or we could say the electric field is tangent to the direction of the normal vector defining those sides. So we got 90-degree angles between the electric field direction and the normal direction relative to the front face, the back face, and the two side faces. So what do we got? I shouldn't say faces, the two sides, the front face, the back, and the two sides. 90 degrees, what do we get? No flux, right? There's no component of the electric field that penetrates through those sides. It's only the top and the bottom. So we've got non-zero, non-zero flux to the top and bottom only. That's great. So we got a closed surface, we use some symmetry arguments, and we've only got two surfaces that we need to consider flux through because the other four surfaces give us zero. So this is what we've got. We composed ourselves this nice block Gaussian surface here. It's really 6 different surfaces, but they encapsulate something, and we go from there. So again, it's just the top surface and the bottom surface that we've got to worry about. So now we go ahead and start applying Gauss's law. So Gauss's law, again, says that the net flux through any closed surface is proportional to the charge enclosed by that surface. And what is that? Well, the net flux through a closed surface, net electric field flux, is then equal to the integral, closed integral over the surface of E hat dot dA hat. That's the definition of flux through the closed surface. And that has to be proportional to the charge enclosed. So we've got Q enclosed divided by permittivity of free space, epsilon 0, constant of proportionality there. So this is what we've got to go with. So when we go ahead and start doing this, what do we have? Well, we've got that the magnitude of the electric field through the top and through the bottom is the same. That's great. And we've also got the orientation of the electric field with respect to the normal vector regarding the surface is, hey, if we just say the normal vector for this top surface is like this, n hat, and the normal vector for the bottom surface is like that, n hat. We've got that the angles, theta top and theta bottom, are equal to 0 degrees. 0 degrees, and what do we know about 0 degrees? We know that the cosine of 0 degrees is just equal to 1. So the point with this is that this dot product vanishes, and we don't need any other extra factor because of weird angles. We've got nice angles here. So we can get rid of this dot product, and we can go ahead and factor that E out because it's a constant value, as we've already argued here. So with this, we've got ourselves E is the integral of the closed surface dA has to be equal to Q enclosed divided by epsilon 0. Now this, I took a little liberty here, and I kind of skipped over a part here, and this is ultimately just the areas of the two surfaces through which there is flux. This dA is only considering as the others yield 0. So it's still through the closed surface, but the only non-zero components are the top and the bottom. So hopefully that's not that big of a deal there. But we can kind of do this. Let's skip this out. That's okay. Let's just say that the net flux across the closed surface, say, let me not skip this out. So that is going to be equal to the integral of E dA top plus the integral of E dA bottom. That's the closed integral, really, over the entire surface. The sides give us 0 contribution, so the only thing that's left over is the top and the bottom, and the dot product vanishes between them. So when we really expand this, I kind of shortcutted this a little bit. So when we really expand this out, then we've got that the net flux, let's just write this. This is it right here, is equal then to E multiplied by the integral of dA top plus E times the integral of dA bottom. E is just the same thing between both of them, right? It's the same magnitude, whether we're on the top or the bottom, because they're both the same distance away. That's great. And then we just have, what is the area of the top? What is the area of the bottom? Well, look at this. The area of the top, we've got this surface. What do we have? This is B by C. That's it. We've got the same thing for the bottom. B by C. So what's the area? B times C for the top or the bottom. So when we got the net flux here, we got sigma flux of E is going to be equal to E times BC plus E times BC. Oh, what is that? That's 2EBC. Where again, those are the dimensions of our Gaussian surface, parallel to the plane of the sheet. All right, so there's our net flux. Fantastic. What do we got to correlate that with? The net charge enclosed, or the charge enclosed by the surface divided by epsilon 0. So we have that 2EBC is going to be equal to Q enclosed divided by epsilon 0, which then allows us to go ahead and solve this out for E, and we get ourselves that E is equal to Q enclosed divided by 2BC epsilon 0. But we could clean that up quite a bit, actually. So let us go ahead and talk about Q enclosed. What is Q enclosed? Well, this is a uniform charge density, right? Q enclosed is going to be equal to the surface charge density, sigma, multiplied by the area of the sheet that's enclosed by that surface. So the area of the sheet is, that's enclosed, is that right there. It has an area of B times C. Whew, look at that. So in the end, this Q enclosed is equal to sigma BC. Surface charge density times the area of the sheet that is enclosed by our Gaussian surface. So what do we get out of this? Well, now we've got ourselves that 2EBC is equal to sigma BC divided by epsilon 0. And what do we get? BC cancels out. Boom, let's solve this out for E, and we get that. The magnitude of the electric field at distance A away from the sheet for the infinite sheet of charge with uniform charge density sigma is going to be equal to sigma divided by 2 epsilon 0. Let's think about this for a second. Where's A in there? Where's A? It's not there, right? There is no A in there. You know what this is telling us? This is telling us that the electric field due to an infinite sheet of charge is constant in magnitude. No matter how far away you are from it, above or below, this is the strength of the electric field. It depends on the surface charge density and, well, 2 times the permittivity of free space. That's it. Constant. So you think about, how do you produce a uniform electric field that has a constant magnitude and direction? Well, you have yourself an infinite sheet of charge. There you go. Or, would you say relatively close to a finite sheet, relatively close to the center and relatively close to it, it's approximately constant. But there's some ways that we could constrain it to be very, very near constant between certain locations. This is what we get out of it. Pretty cool, right? What's left? Are you above it or are you below it? Is the electric field up or is it down? If this was a negative sheet charge, the electric field above would be down and the electric field below would be up. We could tilt it this way and have the electric field this way and this way or that way. Really, it's just the direction of the electric field has to be perpendicular to the plane of the sheet and has a constant magnitude at any distance away from the sheet. There it is, sigma over 2 epsilon 0. Extremely important right here. Don't forget it, because we're going to use it for quite a few things. And it ends up being of great significance. All right. So what we want to do with this then is start doing a couple other little things that correlate with the infinite sheet. And yeah, let's go ahead and do that. Let me erase this, and we'll come back and start doing a little bit more of this. All right, be right back. All right, keeping in the theme with this infinite sheet, what happens if we have more than one infinite sheet? Let's check this out. Let us look at the electric field. Due to 2 infinite sheets with equal and opposite surface charge densities. Plus sigma and minus sigma. All right, so I'm not going to draw these really two-dimensional. I'm just kind of going to take for granted that these are going to be infinite sheets here, but we're going to take one here, and we're going to take another one here. So we've got these two infinite sheets. We're going to say that this one has a surface charge density of minus sigma, and this one has a surface charge density of plus sigma. So there's our two infinite sheets. Great. So what we want to talk about first is, what does the electric field look like due to these individual sheets here? Well, if we take one of the sheets away, we're back just to one sheet, right? And we know that the electric field due to a singular sheet is constant in its magnitude and is directed perpendicular to the sheet, such that it's dependent on whether it's positive or negative, radially outward or radially inward, or just outward or inward, we should say. So for this positive sheet here, we'll start with this one. What does the electric field look like regarding it? Well, above it, the electric field looks like this. Anywhere above it, it has the same magnitude, same direction. So that's right. And then anywhere below it, it has the same magnitude and direction. So I'm just drawing it for two things so we can see that it has the same magnitude. And we've got the blue is E hat plus. And that's, again, due to this positive sheet here. Positive surface charge density. All right. So then what about the negative sheet? Negative sheet charge. What about it? Well, things are just radially, I shouldn't say radially, things are inward towards it. The direction of the electric field points down towards it if it's above, or up towards it if it's below. So we can have the sheet here. We've got the electric field here. It's going to be down, 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 down. And it would be like that here too. No matter how far away we are from it, the electric field would have a downward direction and would have the same magnitude. Here though, below the sheet, we get that it's up, 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 up. And here we still get that it's up, 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 everywhere. Up, up, up. Again, a little bit. So we got down ones here. Down, 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 down. Extending that a little bit. It's a little ugly, but hopefully you get the point there. There we go. So, what does the net electric field look like? That's what we're really interested in here. Let me put purple. So E hat minus. Or minus here. Minus and plus. Fantastic. What do we get? Well, gotta add these two together, right? We add them together and we get ourselves the overall field. Grabbing a pen. All right, got a nice red one here. So what do we get above this negative sheet of charge here? Well, we got the electric field due to the positive ones up, the electric field due to the negative ones down, and because these have the same magnitudes, the same amounts of charge, the magnitudes of the electric fields have to be the same everywhere, right? So we've got magnitude of E plus is equal to the magnitude of E minus is equal to, say, the absolute value of sigma over 2 epsilon 0. Absolute value because the magnitude have to be positive, right? So we just say absolute value sigma over 2 epsilon 0. So what does that mean? That means that everywhere above sigma E hat is equal to 0. Everywhere below sigma E hat is equal to 0 because we have equal magnitudes, opposite directions between the two fields due to these two sheets. Which just leaves us with one point, or one part, I should say. The in-between, right? In-between. Okay, they're in the same direction. Same direction. So what do we get out of this? Well, sigma E hat here is equal to E hat plus E hat minus. It's additive because, again, they're in the same direction. So what does that give us? Well, this, get a little bit messy here, sigma E hat between is then equal to sigma over 2 epsilon 0 plus sigma over 2 epsilon 0, which is then equal to sigma, let's get rid of this. Sigma over epsilon 0. Sigma over 2 epsilon 0 plus sigma over 2 epsilon 0 plus sigma over epsilon 0. And really, generally, what we want to do with this is what we note here, that it's in the j hat direction or upward direction, depending on how you got your coordinate system laid out. But what we really want to get out of this is the net field between two equally and oppositely charged infinite sheets is equal to sigma over epsilon 0. Absolute value, and this is the magnitude. There it is. The direction depends on the orientation of things. We could flip it this way or flip it around and have this plus, this minus. So the direction depends on the geometry of things, but we can always say this is the magnitude, as long as we have plus and minus the same charge densities. So, got two infinite sheets. The electric field's constrained to exist only between those two sheets. Outside of the two sheets, the electric field's 0. So that's pretty cool, huh? We basically just get an electric field at one vicinity in space between the two plates. So what can we do with this? Well, we can imagine that we take two plates that are charged with equal and opposite charge and have them be finite in their expanse, their area, but put them really close together. So if we take, say, two sheets that are fairly large, and have them separated by a small distance here, what does the electric field look like? Well, it looks like this, to a good approximation. That is that the electric field between these two plates is very near uniform in its magnitude and direction, even if they're discrete plates. As long as their spatial expanses are much, much greater than their distance of separation, then we've got ourselves a good approximation. So we've got sheet, say that it's approximately uniform, constant in magnitude and direction. Approximately, what does that mean? Well, that really depends on the actual dimensions of things, but it means that this sigma over epsilon 0 is a pretty darn good approximation for what the electric field is like over the majority of the sheets. Now, as you get to the edges, what you get is edge effects, and you get kind of this bowing of the electric field. But for the most part, if this is minus and this is plus, I guess we should put those in. This is sigma plus sigma, and this is minus sigma. The electric field right in between them looks pretty clean. And as you start getting towards the edges, what you start to get is this little kind of bowing. But usually that's not super significant with respect to the total overall field, so we can use a pretty good approximation. So near the center, or away from the edges, we should say, the electric field behaves much like this. And that's why this is a good good system here. Even though we're using infinite sheets, it gets utilized as a really good approximation for certain situations. And this, two finite sheets separated by some distance that's pretty small, happens to be really important in electronics. And we're going to be talking about this as time goes on. But that's basically that for now. Yeah. So Gauss's law, pretty darn useful. And there we go. Got ourselves another electric field. Another good one, constant. All right, have a good one. Until next, be well.